Okay, guys, welcome back. Got some people in here. Hope everybody's doing okay. I got about a third of you graded as far as the exam, so I should get the rest of you done by this evening for the third exam. Okay, couple other notes. Hold on, let me let some more people in. I just took the COVID shot, so if I start turning into a zombie, we'll talk chemistry in zombie land. Okay. All right. Okay. Let's go on here. We ended up on slide 11, and this chapter again, to refresh your memory, deals with chemical reactions. So before I begin, any questions? Anybody has any questions, comments, concerns, as they say? All right. So there are 6 types of chemical reactions that we're going to talk about. And that's it. Nothing, all the chemistry is out there. These are the most common types of chemical reactions. Okay, rehash it a little bit. Combination reaction. Now, we put it up in generic terms here with the letters A and B in hopes that when you look at a chemical reaction, you can identify the type of reaction, though you may not know what the chemicals are, okay, or maybe not recognize them, but you can see here that there are 2 separate entities, A and B, that come together to form a compound, AB, whatever AB may be, okay? And that is a type of chemical reaction we call a combination reaction. It's combined. A and B have combined to make the species AB. Now, the reverse of that is a decomposition reaction. Notice in the combination reaction, we had at least a minimum of 2 separate reactants to give us a 1 single product, okay? With the decomposition reaction, we begin with a single reactant and we do something to it and we break it apart into components. In this scenario, the components A, B, and C are created, separate components. Decomposition reaction. Now, with respect to combustion, the key points to remember about combustion reaction. Point number 1. When we talk about combustion reactions here at Chem 130, we're going to deal only with hydrocarbons. Those are compounds that consist of nothing but carbon and hydrogen, hence the term hydrocarbons. X represents a number, subscript number, obviously, and Y also. Now, the smallest value X can be for these type of hydrocarbons, these come from a field called organic chemistry, is 1, with carbon X being 1, and the smallest Y value is 4. That gives you the formula for CH₄, which is methane, which is a hydrocarbon, okay? And obviously X can go on all the way to a large variety of numbers. Okay. Now, the other aspect about combustion reaction is for anything to burn, as we all know, is we require oxygen. So oxygen will always be a reactant, okay? Always be a reactant in this combustion reaction, and we're only burning hydrocarbons. And the only 2 products that you will obtain from a combustion reaction of hydrocarbons are carbon dioxide and water. Those are the only 2 products. Yes, I understand if you burn hydrocarbons, like in your vehicle, you will exhaust carbon monoxide, and that is correct. But it happens that way because our engines are not very efficient. Our burning mechanism is not very efficient, and therefore all the hydrocarbons are not thoroughly combusted with oxygen. Hence, we end up with carbon monoxide in our tailpipe. But with respect to Chem 130, when we burn hydrocarbons, the only 2 products we obtain are carbon dioxide and water. And that's why the big issue with burning hydrocarbons is the quantity of carbon dioxide that is created. We burn a lot of hydrocarbons. This carbon dioxide has to go someplace, and it's not going to go out in space. The reason it doesn't go out in space is because gravity keeps everything in. Okay. And so eventually it gets into the atmosphere. And normally that's a good thing because plant life needs carbon dioxide. However, our plant life overall is diminishing. And so we don't have as many, quote, plants to go, to take care of the excess carbon dioxide. So in effect, it gets up in the atmosphere and basically acts as a blanket. And any heat that the Earth absorbs from the sun would normally be emitted back to space, but if it gets reflected back due to this blanket of gases up in our atmosphere, obviously the temperature goes up, the temperature of the Earth. We're familiar with that. Come Sunday, when you go to school and you go early in the morning, your car is nice and in the dead of summer, the car is nice and cool. You shut it down, you come back 4 or 5 hours. What happens to that car? That's pretty hot, right? Yeah, there you go. All right, so that's combustion reaction. The other one is an acid-base reaction. We talked about acid-base reactions in the previous chapter, and that when you have an acid, which is denoted by a compound like HA, A could be any multiple things, but normally hydrogen is written first. That's a pretty good indication that you are dealing with an acid, okay? And then the base deals with the hydroxide polyatomic ion. So they have the compound here, which is an inorganic compound, okay? It's an ionic, I should say, compound, producing the hydroxide. When the proton, the H of the acid, reacts with the hydroxide, you create water. In effect, you neutralize the acid, you neutralize the base to create water. And then you generate the corresponding salt. And salt is not necessarily just sodium chloride, but it could be any metal, depending what M is, and the corresponding A, which is the anion of the acid, okay? To create Ma, which is the salt, okay? Now, along these lines, when we get to these, we're going to talk about how to balance them. And some of these is unfortunately a trial and error kind of thing, but there are some that we do have some specific steps that you can take to make sure that the equation is properly balanced. Single replacement reaction. In order for this to work and to understand, you have to utilize the, from the periodic table, the activity series. And that is right above the solubility rules and right below the periodic table, in between the two. And what this is a listing of metals and their reactivity relative to each other. They're all relative to water. So you see here the H, I should say water, hydrogen and water. All these values, all the relative reactivities relative to hydrogen, okay? And so now I'll have more to say about that in a second. So you can see that lithium is the most reactive metal we have in this series, and gold is the least reactive metal, okay? The species that are in bold and highlighted, those guys are extremely reactive. You simply put those in water and they react violently, extremely. The other ones, aluminum, after the bold, the ones in bold, that means after sodium, when you got magnesium, aluminum, and manganese and zinc, those can react, but they require more aggressive conditions. They require more acidic conditions to get those to react. And we'll have some examples of that too. And then finally, the ones that I've highlighted there in blue, those are the most unreactive ones. And it's a good thing because our copper pipes, if copper is very reactive with water, and they wouldn't function very well as pipes for our plumbing. And gold obviously is the least reactive metal, and that's why it's often called the noble metal, because it's so unreactive. It doesn't mean you can't react it. It can, but it takes very vigorous conditions to do that. Now, if we look at the equation, you can see that we have two metals here. We have the metal M, which could be any of the metals. And then we have the key thing about the metal M, that it is an elemental form. It is an element under the way it's written. It's not combined with anything, okay? And then the other metal is, in this case, A, is combined. It is an ionic compound. It is combined with X, whatever X may be. Now, if this reaction were to proceed as written, you can see that M displaces the A and then produces A back into the elemental state, okay? Where A began as a salt, as an ionic compound, now it is an element. And a good example of this whole reaction is plating. When you plate gold, when you plate copper or whatever metal you want to plate, that's what's happening. It's a single replacement reaction. Okay. Excuse me. The last one, we call it the double replacement reaction. Now, the numbers, the subscripts 1 and 2, that does not denote that there are two M's, okay, or one M. That denotes that there are two different types of metals. So we got metal 1 type, which is bonded to X. And I'll highlight that and give it a red color. And then we have a second ionic compound of metal 2, totally different metal, that is bonded to a different anion. Okay, and we denote that as M2Y. So X and Y are different, M1 and M2 are different. Now, what happens is both of these reactants are soluble in water. Based on the solubility rules, they are soluble in water and therefore are mostly clear solutions. Okay, as you put them together, the relative partners of each other exchange. And so M1 now, which is, let me do M2 because I got the green color. M2 now exchanges with Y, now is bonded with X. You see that? And M1 now is bonded with Y. Now, how do we know if a reaction proceeds or not? Well, what happens is that one of the products that is created, if it is insoluble, then we have a reaction. And so what we utilize, what we utilize is the solubility table right here to tell us whether the product is soluble or insoluble. So for a double replacement reaction, we use the solubility table. And if one of the products is insoluble, then a reaction proceeded, a reaction occurred. If both products are insoluble, then there'd be no reaction. Only when one of the new products is insoluble, then we get a precipitate. It actually gets cloudy. So the two reactants are clear solutions. You put them together and a cloud forms up. And that is an indication of a positive reaction. But they're governed by the solubility in water and aqueous system of the products. It has nothing to do with the reactants. We're looking at the products here, okay? And we're going to do some specific examples. So anyway, here's some specific examples. Here you have an example of a combination reaction where you're taking phosphorus and oxygen, two elements, and you react them together and you form a compound, diphosphorus tetroxide, okay? It's a combination. You have two elements, you end up with one product, okay? And don't forget, we're going to balance it out. So adding a 2 in the reactants balances out the equation, the reaction. Okay, a decomposition reaction. This one here, Fe2O3, aka, anybody remember what the name of that was? Give me a pen here.
Iron oxide? No.
Well, hold on. You are 50% correct. Okay, which is good. And that is the parent name, is iron oxide. But remember, the sweet 16, those are the metals that we knew the constant oxidation number. That meant all of the other metals require Roman numerals. So we needed to put.
Oh, iron 3 oxide.
There you go. Good job. That would be iron 3 oxide. So iron 3 oxide, aka rust. My old pickup, my old truck used to have a lot of iron 3 oxide in it. But if you take iron 3 oxide, where you have the single compound, and you treat it, specifically heat it with high temperature, you actually break it up and you create iron and oxygen. So one key aspect, if we ever find iron rust out in other planets, we can treat it to give us oxygen, because we need oxygen. We need oxygen to breathe, obviously. All right, and iron we can use after we treat it with carbon to make steel and build things with it. Anyway, and don't forget, we got to balance it out. So we need 2 iron 3 oxides to give us four irons and 3 oxygens. The point is that you start off with 1 reactant and you end up with multiple products, a decomposition reaction. Okay. Combustion reaction. All right, first things first. We talk about combustion reaction, and it's burning here. And so one of the key components is oxygen. We need oxygen, right? Oxygen to burn anything, we need oxygen. Then we have a hydrocarbon here. And we recognize it as a hydrocarbon because we have nothing but carbon and hydrogen. Specifically, this is called propane. So the next time you're out there cooking your hot dogs and hamburgers, what have you, think C3H4. Okay. And so that is the reactant, C3H4. And remember, the combustion of a hydrocarbon always gives you carbon dioxide plus water. That's it. Those are the only products you get. Now, with respect to bonding, with respect to balancing these, the previous examples, it was basically a little bit of a trial and error. You kind of put a 2 here, see what that does. You go back and forth, you play with the numbers, unfortunately, until you hit the right combination of numbers so that everything's balanced. With respect to combustion reactions, you don't have to do that because we have very simple, straightforward step. Step number 1, balance. We're going to balance first all of the carbons, okay? And so balance the carbons first, and you can see that we have 3 carbons in the reactant. So we need a 3 here in front of carbon dioxide. So we simply put a 3 there. It balances our carbons, okay? Number 2, balance the hydrogens. Next. All right, so we come over here, we got 8 hydrogens sitting here, and we got 2 on the right side. Well, wouldn't it be true that if we put a 4 in front of water, we end up with 8 hydrogens, and guess what? That balances the hydrogens. So we got the carbons balanced, we got the hydrogens balanced. Finally, the last thing to balance is the oxygen. We got 2 O's over here, okay? But on this side, we have 6 O's coming from carbon dioxide and 4 coming from water. So we have a total of 10 oxygens on the product side. Well, to balance that, we simply put a 5, take half of that 10 and put it in front of oxygen. Why? Because oxygen is diatomic. Okay. And so you put a 5 there, and now you have a total of 10 oxygen atoms. And guess what? You're balanced with respect to hydrocarbons and the combustion of hydrocarbons. So what this tells you is that one molecule of propane requires 5 molecules of oxygen. Quite a bit, huh? That's a lot of oxygen it takes to burn one molecule of propane. So remember that when next time you're cooking your hot dogs, that you're taking up a lot of oxygen, okay, to cook that hamburger. And then you're creating 3 molecules of carbon dioxide and 4 molecules of water, okay? All right, so combustion reaction of hydrocarbons, balance the carbons first, followed by the hydrogens, followed by the oxygens. Okay, let me clear up my mess here. We'll bring in the, and of course I forgot to put in the physical states. And since we're doing a combustion, obviously they're pretty hot temperature, okay? And so the carbon dioxide and the water vapor will both be in the gas phase because we're boiling, we're burning up that hydrocarbon. This in the far left is a 3-dimensional stick and ball model of propane, where the black area represents the carbon and the white color represents the hydrogens. Okay. All right. Next one. Oh, that's the balanced chemical equation. Now, and this is a repeat, okay, a balancing tip, do the carbon, followed by the hydrogen, and at the end, do the oxygen as far as balancing those atoms. And then remember that the products, only 2 products you're going to get are carbon dioxide and water. I state that because, you know, it may be a word problem. So what do you get with the combustion of, write a reaction for the combustion of C3H8? That could be what's given. Well, the 2 key parts to remember, the combustion, that means oxygen's involved. And then looking at the formula, C3H3 means, hydrocarbon only, which means carbon dioxide and water from a product. So now you got the reactant. Okay. And of course, oxygen, you need oxygen to burn it, to combust it. Acid-base neutralization. Now, the key to balancing these reactions is to follow the protons and the hydroxides. Okay, keyword, follow the protons and the hydroxides. Because once you follow those 2, automatically the rest of them get balanced out by themselves. Okay, by default. And always remember this. 1 proton plus 1 hydroxide always gives me 1 water. That's it. Okay, 1 to 1. So if I have 1,000,000 protons, I need 1,000,000 hydroxides, which will give me 1,000,000 waters. Okay, that's it. So if I have 3 protons, I need 3 hydroxides, and vice versa. If I start off with 3 hydroxides, I need 3 protons to neutralize it, which gives me 3 waters. Okay. Let me go here. So rehash. We have the proton, we have the hydroxide, which creates the water, neutralization reaction. And then we have the corresponding salt, which could be whatever metal it may be, and the corresponding anion to give us the Ma salt. Remember, salt is not just simply sodium chloride, okay? Not just that. Salt, Ma, when we talk about salt in chemistry, we're talking about an ionic compound, okay? Because this M could be potassium, could be sodium, could be any of the metals, okay? And the A is not necessarily just chloride. It could be bromide. It could be the acetate. It could be a number of different things, okay? So, all right, so let's take a look at the first equation. And what we have here, let me change the color to make sure we can contrast. So first things first, we see HCl, which tells us, okay, I got an acid. And then we got barium hydroxide, okay? Plus we have 2 hydroxides. What does that tell you? If I see 2 hydroxides, also the other thing, guess what? These guys are aqueous, they're soluble in water. And so when I put them in water, they completely dissociate, okay? And then once they're in water, the protons and the hydroxides are eventually going to combine together. And same with the other corresponding salt that's created. And so I'm going to make, I got 2 hydroxides, so I need 2 protons to cancel out the 2 hydroxides. So I can very quickly put a 2 there. Okay, let me clear this up a little bit. Okay, I got 2 hydroxides. This means I need 2 protons. With that being said, if I have 2 protons and 2 hydroxides, guess what? I'm making 2 waters. All right. Then I have the corresponding salts. I got the barium and the chloride. Now, my recommendation, as always, is to first write them in ionic form. And we know that barium has a +2 charge. Now, why do you want to do that? Because you want to make sure when you put them together, you put them together with the correct number of cations and anions, so they cancel each other out. We know that barium is a +2 metal. It will always have a +2 charge. If you forget that, look at the way it's put together, barium hydroxide. There's 2 hydroxides. The hydroxides each have a -1. That infers that barium must be a +2, okay? But you further confirm that because you know that barium is a group 2 element, and when it becomes ionic, it's a +2 charge. It's a metal, it will lose 2 electrons. The chlorides, they are in, terrible looking Cl. Let me erase that a little bit. In this case, the chloride is a group 7 element, and we know when it becomes ionic, it will have a -1 charge because it's a group 7, it needs 1 electron, it's a non-metal, it's going to pick up 1 electron to give you a net -1 charge. So to put these 2 together, I need 2 chlorides for every barium. So the formula would be BaCl2. Okay. Now let's go back and check to see if things are balanced. The fact that we knew there was 2 protons, 2 hydroxides, gives me 2 waters. Guess what? It balances out my hydrogens. I got 4 hydrogens in the form of water. I got 2 hydrogens in the form of acid and 2 hydrogens in the form of the hydroxide. Hence, it's balanced. I got 2 oxygens in the form of water as a product, and I have 2 oxygens in the form of the hydroxide ion. So my oxygens are balanced. And then I got 1 barium, and then my 2 chlorides, because I got a 2 in front of HCl, balances my chlorides. So I have a balanced chemical reaction. And I balanced it by following the protons and the hydroxides. Okay. All right, let's take a look at the next one. We have H3PO4, and these are one of the acids we talked about that was called phosphoric acid. Okay. Then we have calcium hydroxide. Here we go. We got hydroxide again. Okay. It is a base. And we know that we're going to form water, but we have an uneven number here because we got 2 hydroxides and 3 protons. Now remember when we were putting the formulas together where we had a dissimilar charge, like the iron 3 oxide? The iron 3 had a +3, the oxides have a -2. We looked for a common number to put them together, right? Well, we can do the same thing here. So if I put a 3 in front of calcium hydroxide, which by the way is Tums, all right? And if I put a 2 in front of phosphoric acid, guess what? I balanced my protons, because here I would generate 6 protons here. And over here with the calcium hydroxide, I would generate 6 hydroxides. And guess what? That means that I will create 6 waters. Right? 6 protons, 6 hydroxides give me 6 waters. I've neutralized the acid and the base. Now what's left is the anions, and I'm going to change the color so we know what we're talking about here. We got the metal here, calcium, okay? Well, let's first write it down as ions like we've been doing. So calcium is a +2. It's again, like barium, it's in a group 2 metal, so it would be a +2. If you forgot, look at this, the hydroxide, there's 2 hydroxides, and we know from the polyatomic table, the hydroxides have a -1. So that infers that calcium must be a +2, okay? And then the PO4, again, that's another, what do you call it? Polyatomic ion. In this case, it is the PO4 -3, okay? PO4 -3. And it becomes 3 because the 3 protons that it has, it lost 3 pluses from the protons were lost. And now it has a -3 charge on the polyatomic ion. So those are the 2, the salt, remember the salt that we need to put in there. And so I write them first as ions before I can put them together, because I want to make sure that they are put together with the right ratio. And again, we have a dissimilar charge quantity here, because I got a +2 and a +3 and -3. So what do? We find a common number, which is 6. So I need 3 calcium and 2 phosphates. So I can write the formula as Ca3 parentheses, because I need 2 of my phosphates. Okay. And so now I got my formula. Again, breaking it down individually so we can recognize I got an acid, I got a base, recognize how many protons and hydroxides I have so I can create the right number of waters, and then taking the corresponding salts, the anion, the cation, put them together in the correct ratio. So let me clear my mess here, and we'll bring in the formulas. And this is that one we just talked about. Now, I forgot to put in the first example, barium chloride, the state. Now, if you look at the solubility rule, barium chloride is soluble, hence AQ. Water is being created. It's a liquid. Remember, you are just room temperature. You start off with aqueous solutions. Unlike the previous example where we were at high temperature, the combustion, and we made water as a gas. Here, it's a liquid. It's not a gas. We're not operating at a high temperature. We're not burning anything. So its physical state is a liquid. All right. So with this one here, the product water, again, you create it, so it's a liquid. And how do we know that calcium phosphate is a solid? Well, again, we utilize the solubility rules, and you'll find that calcium phosphate is insoluble, hence the physical state for it is solid. Okay. All right. The takeaway from acid-base reaction: to balance them, follow the proton and the hydroxide to balance everything. And the anions that come with it will balance themselves out by default. Okay. All right, the single replacement reactions. And what was happening here, as I discussed in the other previous slide we first started off, is that we are having two metals reacting with each other. However, each metal is in a different state. This metal M is a solid state. It is an element. Okay, notice it's all by itself. The A, which represents the other metal, AX, it is a compound. It is specifically an ionic compound. So we are comparing two metals, M versus A. Okay, M is in elemental form, the way it's written, and A is in ionic form because it is bonded with X, whatever X may be. Now, if this reaction proceeds, what is going to happen is the M metal will displace, and I'll put that in a different color to see that. The M displaces the metal A that was in the ionic form, begin with AX, and creates A now in the elemental. So it's been replaced. The ionic metal now has been replaced by the other metal. And that ionic metal now is an element. It's a solid metal by itself. This is, and I use the example of plating. That's how plating is done. If you want to plate some metal on the surface, you are starting off with that metal in solution in ionic metal, and then you plate it onto a surface which converts that metal into elemental, into a solid metal. Okay. We use the activity series here to determine whether this reaction will react. Okay. And a very, very simple question to ask yourself is what's happening here is this. The way it's written, this tells me that M is more reactive than A, because that means that M is not very stable being in an elemental form. It is much more stable being in ionic form, MX. Okay. And so what that infers is this, that the most reactive metal prefers to be in ionic form. Therefore, if the most reactive metal is not in ionic form, then the reaction proceeds. If the most reactive metal is already in ionic form, then there's no reaction. The way this one is written, M is a lot more reactive than A. M is not in ionic form, so the reaction proceeds as written. Okay? We'll give you some specific examples here in a second. And like I said, we're using the activity series in which we wrote again here. Notice H again, I emphasize that H is hydrogen. H could, in the elemental form of hydrogen, is H2. But it can also come from an ionic form is, it could be either H plus, or it could be in water, in the form of water. Okay. We'll talk about that in a second here in a minute. All right. So what do we do first? We check the activity series, find out which metal is more reactive. Okay. Then ask the question, is the most reactive metal in compound form or ionic form? If the answer is yes, and then no reaction. If the answer is no, and then reaction occurs. We just switch the partners around. Okay. Then we go back, and like we do before we make the new compound, write them in ions first, so you can put them together the right ratio, and then balance them out. Okay. And of course, obviously, don't forget the state: solid, liquid, gas, aqueous. A lot of these will be, you'll have to look up to see if they're soluble or not. Okay. Then we're back. Let's take this example. what we have here is, change color here. We have zinc nitrate plus sodium metal. Okay, so step number one, going to the activity series, we look for zinc, which is right here, and we look for sodium. Okay, so we can see that sodium is a lot more reactive than zinc. Step number one. Okay, number two, is sodium in I want to say ionic form? Is it an ionic compound? Okay, is the question. And in this case, no, it's an elemental. So the answer is no, it's not an ionic compound. And so number four would be yes on the reaction. Reaction proceeds. Okay. So sodium is a lot more reactive than zinc based on the activity series. Sodium is not in ionic form because that is, you look to see that if the most reactive metal is in ionic form. And since it's not in ionic form, then reaction proceeds and you switch the partners. So zinc and sodium switch it up. So zinc now becomes elemental zinc and sodium becomes ionic. Okay. Based on what we just did. So let's do this. We'll write the formula, the equation. Okay, plus sodium. And zinc is going to now become elemental form because sodium is a lot more reactive. Now, we need to first, again, as I stated, write the other products that are in ionic form first. So we know sodium is a +1, it's in group 1, okay? And we use NO3, the nitrate, so we know from the polyatomic ion that table, from the polyatomic ion table, the periodic table, that nitrate has a -1, okay? So I can put sodium and nitrate together as a 1-to-1 based on their charges. And that's why I said to write them out first with ions before you put them together. And so the formula for sodium nitrate is that. Okay, couple of things. We know that zinc nitrate is soluble in water. So that's why it's aqueous, is given to you right there. And we know that sodium metal is solid. Okay, so let's do the physical states. We know that zinc is a metal and it's a solid because there's only one metal that is a liquid. You might go back and refresh your memory. So zinc is a metal, is a solid metal. Okay. Sodium nitrate. Question is, okay, what's the physical state? We are dealing with an aqueous system here. No, sodium right at the top. Look at your solubility rules here. First one in the left column. Anything, remember the top four there, the big four, sodium. Anything bonded with sodium is soluble. That's all you need to know. You see sodium, it is soluble. And so you already got the physical state of the product. Now it's a matter of balancing them, okay? My suggestion here, when you have polyatomic ions, follow the polyatomic ions to balance your equation. We have nitrate to begin with, and there's 2 of them, okay? So all we got to do is put a 2 in front of sodium nitrate. That balances out my nitrates, my NO3, because I started with 2, now I still got 2. What that does is kick up my sodium, right? Sodium goes up. Okay, no problem, because sodium over here is an element, it's all by itself. I just simply put a 2 in front of sodium, and that's balanced. So go back and check now. I got 1 zinc, 1 zinc. So my zincs are balanced. I got 2 sodiums here and 2 over here, they're balanced. And I got two nitrates. Remember, the polyatomic ions keep them together as packets. It's much easier to balance them. I got two over here, and guess what? I got two over here also because I got a 2 in front of sodium nitrate. So I have a balanced chemical reaction here. All right. Let me rehash all the steps we just did. We were given a reaction. Change the color. And we have sodium nitrate and sodium. So, excuse me, zinc nitrate and sodium. So step number 1 was to look at the metals, regardless of what state they're in, whether they're in the compound or an element, and compare the reactivity, the activity series of those two metals, which we did. And we found that based on the activity series, that sodium is a lot more reactive than zinc. Okay. Go back to the equation. Is the most reactive metal in ionic form? Is it in the compound? In this scenario, the answer is no. That means the reaction proceeds and we just simply exchange metals. Now, prior to, and that zinc that started off in ionic form automatically now becomes the elemental form. So we can quickly put zinc all by itself, which leaves now the sodium and the nitrate. Well, before we put them together, write them out in as ions first so that you can put them together with the proper ratio. And doing that, you can see it's a 1-to-1. So my formula is simply sodium nitrate. Okay. Now, at this time, you can go and put the physical state, because we know based on the solubility rule that anything bonded with sodium is soluble. So it'd be AQ, because we started off with the AQ solution. Okay, you see right here, we're given, this is an aqueous solution. All right. So we check the solubility, the physical state. We know that zinc, elemental zinc, is a solid. It's a metal. That is, all the metals are solids. There's only one liquid metal. Okay. And then sodium nitrate is aqueous solution because it's soluble. Now, after we've done that, now we balance it, and balancing these, when you have polyatomic ions, follow the polyatomic ions. So I followed the nitrates. I see that I got 2 of them. So I come over here to sodium nitrate, put a 2 in front of sodium nitrate. That balances out. That kicks up my nitrogen. I go back to reactants, put a 2 in front of, not nitrogen, sodium. Put a 2 in front of sodium. That balances my sodium. And go back and check. And I got a balanced chemical equation. All right. So let me clear my mess here, and let's bring on the good writing here. Rather than that chicken scratch I put up there. So we got zinc nitrate aqueous solution plus a sodium, okay, which is a solid, elemental sodium, to give us sodium nitrate. The sodium metal being more reactive than zinc, sodium being more reactive in zinc, prefers to be in ionic form than free metal by itself. Okay, and hence that's why this reaction proceeded. Obviously, we wouldn't write Na parentheses NO2, because hopefully by now you know that the NO3, which is the nitrate, has a -1 charge. You also hopefully know that sodium is in group 1 and only has 1 valence electron, and it's going to lose that 1 valence electron. The way it's written here is Na parentheses NO3 parentheses 2 infers that sodium has a +2 charge, but that's not possible because it doesn't have enough electrons for 1. It's not in group 2, it's in group 1. There's only 1 valence electron. It will only lose 1 electron. Okay. All right, here we have this one. Strontium bromide plus aluminum. Okay. Step number 1. Compare the metals as far as reactivity. And so we have strontium right here, and aluminum right here. And so that tells you that SR is a lot more reactive than aluminum. Okay. All right. Question number 2. SR ionic. Is SR is the most reactive metal in an ionic compound form. Okay. And guess what? Look what that says. Strontium bromide. So the answer is yes, it's already in ionic form. And that implies NR, no reaction. Okay, no reaction. Because the most reactive metal here is already in ionic form. So it won't react. Okay, so the correct answer here will be NR. Keep in mind, if it doesn't go as written, guess what? If I rewrite it a different way, it will react. If I say, would this reaction react? Aluminum bromide plus strontium. What would you think? For aluminum bromide plus strontium, do you think that reaction will proceed? Go through the steps we just went. Which one's most reactive? This is more reactive. Strontium is more reactive, just like we did for the first one up there. Okay. Second question, is the most reactive metal in ionic form? In this case, no, it's not. That means that this reaction will proceed. So this aluminum becomes aluminum solid. Plus strontium becomes, now we have SR, which is a +2 because we know it's in group 2. And then the bromides are -1. Okay. And so its formula would be SR Br2. Okay. And that would be the reaction. So the opposite would be true compared to up here. Okay. So if the reaction doesn't proceed as written, like in the example up on top, that means that the opposite reaction would occur. Okay, because strontium is still more reactive than aluminum, regardless if I write it as SRBr2 or I write it just SR. Okay, no reaction. Okay, here's the question: aluminum versus HCl, hydrochloric acid. All right. Well, what we're doing here, we are comparing aluminum with hydrogen, and so we go to the activity series. Look where aluminum is. Look where hydrogen is. It's in parentheses. So what does that say? Aluminum is a lot more reactive than hydrogen. You all see that? I said you all. Aluminum is right there, and there's hydrogen. And so aluminum is a lot more reactive than hydrogen based on the activity series. Okay. Second question, is the most reactive metal in ionic form? And the answer to that is no. Aluminum is in elemental form. So that reaction will proceed. So hydrogen, which right now is in I didn't want to do that, but hydrogen, which right now is in H+ form, to get it to elemental form, guess what? It is simply H2. Yeah, that's the elemental form of hydrogen. Okay. And so aluminum is going to replace the hydrogen. And so we need to first write them in ionic form before we put it together. So aluminum is, we know, is in group 3. So when it becomes ionic, guess what? It has a +3 charge. And we know that the chlorides all have a -1 charge. Okay, that means we need 3 of them. And so our formula would be aluminum chloride with 3. Okay. Let me clear that up a little bit. Okay. And aluminum chloride, we know it's soluble, again, based on the solubility, hence HQ. And H2 is a gas, okay? So here's an example of a metal. Look at where aluminum is. It's not one of the highlighted metals, the first, 4 or 5 of them, up to lithium through sodium. And I stated, once you get in magnesium, aluminum, and so forth, to get those to react, you got to have more aggressive conditions, and more aggressive means an acid solution. Okay. And that's what's happening there. So you got aluminum, aluminum chloride, which is aqueous, and then hydrogen gas. Okay. Now there are YouTube videos concerning these reactions written by Dr. Kim. Please, by all means, go up there and listen to them. We also got them in the module there for you. So not only you have my stuff, you also have Dr. Kim's stuff. All right. Oh, and then of course, balance it out. Unfortunately, one of these here, there's no clear-cut way to balance it out. You got to do a trial and error on this one. So give it a shot, see what you come up with, but you should come up with 2 aluminum, 6 hydrochloric acid, 3 aluminum chloride, and 3 hydrogen gas. Okay. A word about balancing chemical equations when you're putting coefficients in there. It is possible that at times that when you're balancing and you finally come up with the numbers, you end up with, let's say, 4 here, 12 here, 4 here, and maybe 6 here. And that happens sometimes. You're playing with the numbers and you end up with these greater numbers. But thing to remember is once you're done with the balancing step, check it. Just like in mathematics, bring it to its lowest terms. So yes, if 4 aluminum, 12 hydrochloric acids, 4 aluminum chlorides, and 6 hydrogen gases, yes, they are balanced, but by convention, you want to present your balanced chemical equation with the lowest common coefficients possible. Okay. So in this case, everybody here is basically divisible by 2. 1, 3 over here. So, all right. Let's clear this one. We're 28. So the flow chart with respect to activity series, you look at it, you compare the most reactive metal, you look at the activities, you determine which one is the most reactive metal. Ask the question, is the most reactive metal in salt form? If the answer is yes, then there's no further reaction. If the answer is no, then yes, there is reaction, and you just exchange the partners, remembering for the other salt to write them out first as ions before you put them together. So you can put them together properly with their correct ratio. Okay. Now, here, the double replacement reactions. Thing about these reactions, as I mentioned before, is they require you to use the solubility rules to determine whether a reaction proceeded. Because in this generic example here, you can see that the combination of AY, all right, which is basically, both reactants are soluble in water, and they just essentially just exchange partners here, okay? The A combines with the Y, the B combines with the X. Now, based on the solubility rules, AY in this scenario is solid. It's insoluble, therefore its physical state is S, therefore a reaction proceeded, okay? BX, based on the solubility rules, say that it's soluble. So we put AQ. Now, at any one time, if, for example, we go through the solubility rules and we find that AY was in fact soluble and BX also is soluble, then we have no reaction. Point is, for this reaction to know if it's going to go, we simply exchange partners, but then we look at the products only to determine whether the reaction proceeded. Because we know that the reactants are both going to be soluble, both aqueous solutions. It is the products that we're concerned about. And if any one of these is soluble, insoluble, then we have a reaction, okay? If they're both soluble, then no reaction. Yeah, so this solid form, because it's being insoluble, is we call it precipitation. So a double reaction is a precipitation, can also be called a precipitation reaction, okay? And there's a solid that forms, and obviously the solid is called a precipitate, okay? Solid forms, you get a reaction, and no solid forms, and no reaction. We're gonna look at the solubility rules. Now, I know it's been a while since we looked at it, so I'm going to very briefly go over it quickly just to refresh your memory. Remember, we have two columns here, okay? We have the left side column, which is the soluble column. Now, with respect to number one, notice that all of them are cations. So anything, any anion, any negative what's the word? Any negative charge ion, any anion bonded to these four, always soluble, 100% of the time. All right, just those four. Now, with respect to the anion, the acetate, and the nitrate, in these two anions, regardless of what the cation is, regardless of what the plus charge is of what it's bonded with, it is soluble. So potassium's, obviously potassium acetate is soluble, but copper acetate, magnesium acetate, any of the other metals is soluble. The same with nitrate. Aluminum nitrate, soluble, any copper nitrate, soluble. With respect to the halides, and those are the chloride, the bromide, and the iodide, these three right here. Most of the time, they are soluble regardless of what the partner is. The only exception are these three. If you have silver, mercury, or lead with any of those three halides, then it is insoluble, okay? That means that everything else, all the other billion examples out there, are soluble. The sulfate ion, the SO4 and the -2, normally 100% soluble with everything except if it's bonded to calcium and strontium or barium, silver, or lead. Those five sulfate compounds are insoluble. Otherwise, all the other thousands of compounds, sulfate compounds, are soluble, okay? Now remember, when we talk about soluble, insoluble, soluble means it totally goes in solution, roughly 100%. Insoluble means not so much, maybe 1 to 5% goes in solution. You still got the bulk of it combined together, but there is a little bit of ions in solution, okay? Now, with respect to the right side column, which is the insoluble column. Insoluble column. If all the carbonates, CO3 minus 2, regardless of what they're bonded to, they are insoluble unless they're bonded to the big four. If you forgot what the big four was, lithium, sodium, potassium, and ammonium. If those four are bonded to carbonate, there's only 4 examples of carbonate compound that is soluble. Everything else, insoluble. Chromate and the phosphate, same scenario. It is essentially insoluble with anything except the big four. Always be soluble if they're bonded to the big four. Okay. So now it brings you to the sulfide. That's the S-2 ion. Normally, 100% of the time, they're insoluble, except if they're bonded, like the previous example with the big four, and they're bonded with calcium, strontium, or barium. So there are only 7 examples of sulfides that are soluble. All the other examples are insoluble. Okay. And then finally, the hydroxide, same thing. Normally insoluble unless they're bonded to the big four and also to calcium, barium, and strontium. Again, there's 7 examples of soluble hydroxides. All the other hydroxides are insoluble. Okay, so that's a rehash of the solubility rules. Okay, so with that being the case, let's take a look at this double displacement reaction. We need to determine whether this reaction would proceed. And we do that by determining whether the products are soluble or insoluble. Okay. Now, first thing is this. We got barium nitrate and magnesium sulfate. What's going to happen is the barium is going to exchange with the sulfate. Okay. And obviously the magnesium is going to combine with the nitrate. All right. Now, before we put any of these together, let's first write them in ion form to make sure that we put them together in the right ratio. All right, so barium is in group 2 element, and so it will be a +2. If we forget, note this, nitrate, polyatomic ion, each one has a -1. There's 2 of them, so that infers that barium must be a +2, okay? The sulfate, using the polyatomic ion table, the sulfate you'll see to have a -2 charge. All right, magnesium, also a +2, the group 2 element, and then the nitrate, NO3, has a -1, okay? Well, if I'm going to combine magnesium nitrate, guess what? I need 2 nitrates. So let's write the formulas now of the new products. So we got barium sulfate. We can simply put those together as a 1-to-1 because we get a +2 and a -2, 1-to-1. Magnesium nitrate. Well, I'm going to need a parentheses for the nitrate because I need 2 of them to balance out the +2 of the magnesium. Okay. Now, once we got the formulas together, now the next step is to determine the solubility. We got a sulfate here. We go down here to the sulfate region, which is number 5. And normally it's soluble, right? Except calcium, strontium, guess what? Barium, silver, and lead. So barium sulfate is insoluble. And so we have a solid here, okay? Then we look for the solubility of the nitrate. The nitrates, look at number 3. Regardless of what nitrate is bonded to, always soluble. And since we're doing aqueous, and then this is AQ. So guess what? We have a positive reaction, okay? We have a positive reaction. So step number 1, when you put them together, first write them in the ions before you put them together, then put them together with the right number of ions. Okay. Now, then the step after that is to look at the solubility and see if the products are soluble or insoluble. If both of these would have been insoluble, then you could have stopped and say no reaction. But the fact is that one of them is insoluble, and therefore you do have reaction. Okay. So the next thing is balancing. Well, with respect to polyatomic ions, which we have here, follow the polyatomic ion, and everything else will balance out by default. So we can see we have two nitrates to begin with in the form of barium nitrate. Guess what? We have two nitrates at the end in the form of magnesium nitrate. So the nitrates are balanced. Sulfate, we got one sulfate in the form of magnesium sulfate, and we have one sulfate in the form of barium sulfate. So the sulfates are balanced. Now it's easier, I said, the polyatomic ions, to follow them as a unit. Yes, you can follow all the nitrogens and all the oxygens, but that's a lot more accounting. And it just makes it easier just to follow the unit itself, the polyatomic units themselves. We got one barium and one magnesium, and lo and behold, guess what? We got a balanced chemical equation. It balanced by itself just by default, because of the respective charges of the ions. Okay. All right. Let's do one more. All right. So again, we got two aqueous. Analyze the reactants. We got two aqueous reactants here. Okay. We're going to exchange partners, and so write the ions to make sure you are putting them together correctly. And we're dealing with lead 2. Now, how do we know it's lead 2? Because we know the nitrates are all -1, and there's 2 of them. So that infers that lead must be lead 2. The iodides. Iodides are group 7, excuse me, and non-metal. It's going to gain 1 electron. So you have a -1 for the iodide. The potassium, we know it is in group 1. It's going to have a +1 charge. And then the nitrates, as we talked about, have a -1. So I wrote all the ions here, and I just put them together because I put them together in a manner so they're going to be close to the new partners. So the lead with the iodide, potassium with the nitrate. Now I put them together. I need 2 iodides. So my formula now is PbI2. And then potassium and nitrate, it's a real simple 1-to-1. Okay, so I can just do that. Okay, so those are my 2 new products. Now, once I've done that, I go check the solubility of my products. I got lead iodide. The fact that you got iodide, this is halogen number 4. Normally, they are soluble. However, when you got the 3 metals, silver, mercury, and lead, guess what? Insoluble. So that means we got an S right here. There's supposed to be an S for solid. Potassium. You don't even have to analyze that, right? Because you got potassium right up front. Potassium is one of the big 4 automatically. Soluble, aqueous. Okay. So now we got the physical states. The fact that one of these products is soluble, insoluble means we got a solid, which means we got a reaction. Now we're going to balance it. Okay. Again, follow the polyatomic ions. All right. We have 2 nitrates to begin with over here. Okay. But we end up with 1 as a product. Guess what? Just put a 2 in front of potassium nitrate. Now you balance the nitrates, which means that kicks up the potassiums, no problem. Put a 2 in front of potassium, okay? Which then kicks up the iodide. But by default, you have 2 iodides because there's 2 needed for every lead +2. And guess what? You have a balanced chemical equation. Let me clear up this mess here. And you end up with that. Okay, and of course, we balanced it. All right. Oh, I think I got over my time here. We are on slide 27. Let me see here.